Okay, thank you. So I'm Carina Furusho Percot again, and I'm one of the PIs of this sub-project with Stefan Collett and Harjan Hendricks Fransen. But all the results that I'm going to show today for you were made by Thomas Pomeon, who unfortunately could not make it today. So I'll start with a quick overview of the work that we carry out here in our research group in Jülich and our role within the whole research unit RealPEP. And the next, I want to describe our methodology and particularly why we're using ParFlow, and then present some preliminary results for our first case study. And then finally, I want to talk about the challenge that we've set to ourselves in RealPEP of evaluating precipitation improvements with all the questions that still remain open, and I really welcome your insights on this. So as Silke has presented in more detail in the first session of the conference, RealPEP gathers meteorologists and hydrologists to work together on improving flash flood predictions in a very integrated way. And we are the sub-project downstream, as all the products being developed in the other sub-projects will converge and then serve as inputs for our hydrological model. And then we are also literally focus on what is going on downstream of the catchment, as our goal is to improve river discharge forecasts, especially these flash flood lead times. And now, even if we all agree that great part of the uncertainties come from the others, from the precipitation forecasts and nowcasts, they are certainly not the only ones. And so we also question the simplifications and uncertainties of the hydrological models themselves. So the work that we carry out here in the Center for High Performance Scientific Computing in Terrestrial Systems are described in our website, where you can see all the projects involving the terrestrial system modeling platform. You can also find 10-day forecasts updated every day using the fully coupled system with variables like precipitation, temperature, but also runoff and plant available water content for the whole European domain. And here you can also see we have in final resolution our region, North Rhine-Westphalia, and preliminary results of the ADAPTA project shared by Alexander Belflam, who applies ParFlow over the German territory in a 500-meter scale. So ParFlow is part of this terrestrial system modeling platform, which is the product of this holistic approach to model the geoecosystem from groundwater to the atmosphere. And it's also coupled to the parallel data simulation framework, which will allow us to assimilate discharge and soil moisture in a very efficient way further in the project. But for the results I present today, we use ParFlow standalone, which has a 3D variably saturated flow based on Richard's equations, and a 2D overland flow based on the kinematic and diffusive approximation. So now you may be asking why ParFlow, especially if you've worked close to operational flood forecast services using mostly lighter conceptual models and wondering why should we solve computational demanding equation for nowcasting, right, which is a very time-sensitive application. So first of all, ParFlow can be used in a very parsimonious, lighter way without any calibration, which is convenient for ungauged catchments or where there isn't a very long time series of discharge available. And moreover, a distributed high-resolution setup of ParFlow can better benefit from the improvements of precipitation products. Well, this is our hypothesis. And it is indeed harder to capture better spatial variation of precipitation inputs using, for example, lumped models, or to distinguish better inputs when the model calibration can adapt the model to the input bias and so on. So therefore, our methodology is to use a very parsimonious setup for ParFlow with input data that are globally available to ensure transferability of this framework to any other catchment and consider model uncertainty by using an ensemble of physically possible parameters, again, with no calibration. So for testing the methodology, we want to ask the following questions. So first, how is the performance of ParFlow for hindcasts and nowcasts? Is it good enough, fast enough? Is ParFlow's performance indeed sensitive to these different precipitation products? So for that, we tested in the beginning 2 different precipitation products, QPEs, and we perturbed 2 key parameters of the model and tested the effect also of the first QPN, the nowcast product that we received in the project. And all these results, plus a comparison of ParFlow to the conceptual HPV model, were recently published in this paper here below. So now here's the scheme of the experiments that will be presented today with this ensemble, the hydrological ensemble of 12 members for the hindcasts and 0 precipitation nowcasts as well. And then for the nowcasts, we have 5 scenarios. So we'll have, in the end, 60 nowcast ensemble members to account for all these uncertainties. And our first case study is a small flash flood prone catchment near Bone. And you can see here the location of the catchment as well as the range of the radars that were used for these experiments in red from Guilford Bond and Terrain Observatory. The model resolution is 50 meters horizontally, and vertically we have 4 layers going as deep as 4 meters. And the model is running every 5 minutes. And for that, we used 48 cores to run ParFlow, but recent developments will allow us to run it on GPU much more efficiently. So the case studies, we have here the cumulative total catchment precipitation time series that illustrates how tricky it can be to compare precipitation inputs in hydrology. We can't say if one of them is overestimating, has an overestimation tendency because it depends on the event. And in 3 of the 5 cases, they are very, very similar. And probably a lumped model would give similar results, right? And so with ParFlow here, for the same 5 events, we have three of them where it flooded. So it goes above this red dashed line of 15 cubic meters per second. Here in 2010, and then 2013 again, and here the last one in 2016. The other 2 ones are there, but we didn't have the bank, it didn't reach the flood. So we can see that the ParFlow ensemble in blue is bracketing pretty well the observed discharge, which is the black line here as reference. And even without calibration, but it's really hard to see, like side by side, the difference between the input. And so that's why we've also calculated some scores here. So if we look at the ensemble mean performance, they are also some very close when you look at each event. But we can see, nevertheless, the differences here when we look at the CRPS, the continuous ranked probability score, and also the amount of observations that it's bracketed for each event. So probably these differences come from the spatial distribution of the rainfall that the model is able to capture, right? And here Hadolan outperforms Expo in most of the cases, but the sample of 5 events is definitely too small to allow any robust conclusion. So here we can see the nowcast, the gray nowcast ensemble evolving, and it also brackets the observation discharge pretty well and in advance. And these 2-hour nowcasts take around 30 seconds to run on 48 cores, but it depends on the rainfall as well as the model resolution, of course. And if we compare the 0 precipitation forecast, and in a moment just before the flood, we can see the added value of the QPN, as when you use only the QPEs here in the hindcast in blue, we see that the model wouldn't be able to capture the bankful discharge. And so to conclude, ParFlow has a good performance as the ensemble captures most of the observed discharge without calibration and within an acceptable runtime. When we run a 24-hour simulation, we have 6 minutes wall time for now. And it was also encouraging to see that the precipitation input has different scores of the ensembles, as they can help then to rank precipitation inputs further in the project. And also, we had significant lead time improvements using precipitation nowcasts. So the model is able to do this. But we are aware that there are still many important things missing to be able to provide this expected hydrological evaluation of precipitation improvements, the feedback that the other groups are waiting for. We need first to extend the evaluation over much more catchments and over longer time series to have statistically robust conclusions, as Elena was also discussing previously. We have to explore other scores to consider timing, but also magnitude of discharge nowcasts. But then, as Elena and Marco were also discussing, when we talk about the magnitude, we have to consider the uncertainties of the stream flow observations as well. And we didn't have enough information on the rating curve for Melon, but we'll do this for the other catchments. We have more information from the Tirreno Observatory. And with this data, also, even if we risk smoothing out the differences between the precipitation inputs, we really have to include data assimilation, like discharge and soil moisture for the hydrological model, because it really improves flood forecasts. So the last very important thing that is missing for us is potentially one of you or one of your students, because we're currently hiring hydrologists to take up all these exciting challenges. And you can find more details in our ULISH Research Center website, but I can also share the link with you and discuss in the video chat this afternoon, if you're interested. So we acknowledge the FDA for funding the project and also the Earth System Modeling Project by providing computing time on the supercomputer jewels that we used from the ULISH Supercomputing Center. And I thank you all for your attention today, and I'm looking forward to your inputs and questions. So if you have any questions.
Perhaps I can give it the start.
Yes.
You mentioned the soil moisture models. I just wonder, NWP is running a soil moisture model, and we have some data assimilation for soil moisture as well, but it is driven by the atmosphere, basically, by 2-meter temperatures. And I asked myself, what type of soil moisture models would you be able to use? Do you need your own one? Do you need to integrate it with your discharge model? Can you say a word on that?
Yes, of course. Actually, it would be soil moisture assimilation. We would update our variables of soil moisture within the hydrological model using real-time data, actually, with PDAF, the parallel data simulation.
So it would be a model really integrated into the tar flow.
Exactly. The problem, we haven't used this yet to this rainfall comparison, because the risk is that we will see less difference between rainfall inputs as well. But we definitely have to use it in the project.
Well, I might add to this. I mean, the main difference from a soil model in a weather forecasting framework is that the soil model there is not really connected hydrologically to a river, right? I mean, that's the difference. And we really basically transfer the water via the soil, via the groundwater, then also back into the river. And that, of course, also contributes to the, let's say, to the discharge.
Yeah, so I'm just quite interested in it because in the NWP framework, you have, of course, a coupling between the atmosphere and the soil moisture. And you also have measurements of different types. You have direct measurements using Landsat or something like this, is a satellite-based measurement. And then you also have, which only you can see the top surface, of course. And we also have indirect measurements by 2-meter temperature changes over periods of time, which of course are strongly influenced by the flow, by the soil moisture and the flow through the layers. And it would be very interesting to see how this compares to your models and how to improve the overall system, of course.
Thank you, Roland.